Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Welcome to the Deep Dive. Today, we are strapping in for a pretty wild ride. We're exploring the most powerful space weather event we've seen in more than 2 decades.
We really are. This was a true cosmic punch that Earth took back in May of 2024.
Right, and it wasn't just spectacular to look at. I mean, the photos were incredible, but it was scientifically just a gold mine.
A total gold mine.
Okay.
We're unpacking a whole stack of sources today, all focused on what's called the Mother's Day storm. It happened on May 10th and 11th.
And space weather scientists have a name for it, right? Superstorm Gannon.
That's the one, Superstorm Gannon.
Mm-hmm.
It was classified as a G5 storm, which is, the absolute highest level of geomagnetic activity you can have. And the data it gave us, it's fundamentally shifting how we think about planetary defense.
I think we all saw the headlines, and maybe some of you even saw the auroras, which were stunning. But the real story, the one we're digging into, happened in the invisible shields around our planet.
Exactly. Our mission today is to figure out why this storm, the strongest in over 20 years, gave us a data set we've just never had before.
It's not just about the storm's initial hit, is it?
No, not at all. The core mystery here isn't just the immediate violence of it, but the lingering aftermath. For the first time, we have this incredibly detailed look at how the superstorm assaulted Earth's protective layers.
Specifically the plasmasphere.
The plasmasphere, exactly. The initial compression was just brutal. We're talking 9 hours of intense pressure.
Right.
But then the recovery was so strangely slow, it took 4 days.
And 4 days of disruption, that means 4 days where our satellites, our infrastructure are vulnerable.
That's the risk.
So we're going to walk you through that timeline. First, how this huge protective layer got squeezed to about 1/5 its normal size. And then the really critical part, how these invisible chemistry problems in the atmosphere, a thing called a negative storm, created this massive 4-day supply chain problem that left our technology totally compromised.
It's a fascinating story of physics and chemistry on a planetary scale.
Okay, so let's set the stage here. Superstorm Gannon. When we talk about a geomagnetic superstorm, we're really talking about something at the extreme end of the scale. How rare was an event like this?
I mean, truly, truly rare. Based on all the historical data, a G5 level storm, which this was, happens on average only about once every 20 to 25 years.
Wow.
Yeah. We haven't seen anything this intense since the famous Halloween storms back in 2003.
And I remember those. They took out a bunch of satellites, right?
They did. Cause all sorts of problems.
Yeah.
So this Gannon event was in that same league.
So that establishes the rarity. Now let's get into the cause. What was it on the sun that shot this once-in-a-generation blast of energy right at us? It's not just a solar flare, is it?
No, it's much, much more than that. The storm was triggered by a whole series of massive, powerful eruptions from the sun's atmosphere, and they were all timed very closely together.
Eruptions of what, exactly?
We call them coronal mass ejections, or CMEs. You have to picture these colossal bursts of material. Basically, the sun just hurled billions of tons of highly charged, magnetized plasma straight towards Earth.
Okay, so what's the difference between a normal CME, one that just gives us some nice auroras up north, and this kind of monster that can compress our entire magnetic field?
Right, it really comes down to a few key ingredients. First, you need speed.
Speed.
The CMEs that created Gannon were moving incredibly fast, well over 1,000 kilometers per second. That speed creates this immense pressure when it hits our magnetosphere.
Okay, so speed is one.
Second, you need mass. It was billions of tons of this stuff, which ensures it's not just a quick hit, it's a sustained push.
But there's a third thing, right? The really critical factor that turns a fast CME into a crushing storm. It's about the magnetic field, isn't it?
Absolutely.
Yeah.
It's all about the magnetic field orientation of that incoming plasma cloud. We call it the Bleds component.
The Blez component.
So the sun has its own magnetic field, and it's embedded in this CME cloud. Now, if that cloud's magnetic field lines are pointing north, they line up with Earth's magnetic field, and things are, relatively calm.
They sort of glance off each other.
More or less.
Okay.
But if the cloud's magnetic field, the Braz component, is pointing south, it directly opposes Earth's northward pointing field lines.
And when those opposite fields meet, they don't just bounce.
No, that's when the fireworks happen. They undergo this violent process called magnetic reconnection.
Which is like what? A short circuit?
It's exactly like a short circuit, but on a planetary scale. This reconnection just rips open the boundary of our magnetosphere. It's like opening a door and letting a massive amount of solar energy, momentum, and charged particles pour directly into our environment.
And the Gannon storm had that southward buzz.
It had a sustained, powerful, southward-pointing buzz, and that's what allowed for the maximum, let's call it, coupling between the solar wind and our magnetosphere. It was the perfect storm.
So the storm hits on May 10th, 2024, and this intense magnetized plasma just slams into us. And our protective layers react pretty much instantly.
Almost instantly.
Yeah.
The major compression phase, the big squeeze, only lasted about 9 hours.
9 hours. That rapid energy transfer just tells you how powerful that southward bruise must have been.
It really does.
Oh.
But before we get into the details of the squeeze, we should probably define what exactly got squeezed. We need to talk about the plasmasphere.
Right. And for everyone listening, this isn't the same thing as the magnetosphere itself, right? It's a structure inside of it.
Exactly. It's an inner structure, but it's vital for our protection.
Okay, so let's break down the shield. What's the plasmasphere made of, and why do we care so much if it gets damaged?
The plasmasphere is this dense, kind of donut-shaped region of pretty cold plasma. So low-energy charged particles, mostly hydrogen ions and electrons. It sits deep inside the magnetosphere, and it co-rotates with the Earth.
And its job is?
What?
A buffer.
A buffer is a perfect way to put it. It stabilizes the electric and magnetic fields in that inner region. And critically, it absorbs and sort of neutralizes a lot of the less energetic particles that try to get into our environment. It's a key part of our fielding.
So what happens to all our satellites that live in or near that region if the plasmasphere is compromised?
2 bad things happen. First, the protective environment is just gone. So satellites are exposed to much higher energy particle radiation that normally gets filtered out.
And the second thing?
The second is often more insidious. The outer boundary of the plasmasphere, we call it the plasmapause, is a region of instability. When that gets compressed, it moves closer to all those vital geosynchronous orbits.
Where our communication satellites are.
Exactly. And the extreme changes in the electric fields there can cause something called satellite surface charging. It's like giving the satellite a dangerous static electricity jolt. It can totally disrupt its electronics.
So Superstorm Gannon was basically a brutal, real-world stress test for this entire region.
The ultimate stress test.
Okay, so let's unpack that stress test. We know the plasmasphere is this vast charged bubble in its normal state. Let's get into the specifics. What are the baseline measurements? How big is it normally?
Under normal, quiet conditions, it's huge. We define its outer boundary, the plasmapause, as the point where that plasma density just drops off sharply.
And where is that usually?
That boundary typically sits about 44,000 kilometers above the Earth's surface.
44,000 kilometers.
Right. It's about 6.6 Earth radii. It's a really comfortable, immense buffer zone.
And just for context, that 44,000 kilometer baseline is well beyond the orbits of our most crucial communication satellites. Geosynchronous orbit is what, around 36,000 kilometer?
That's right, about 35,786 to be precise. So the plasmapause normally provides this crucial protection around that whole GEO belt of satellites.
But during Gannon, that high-speed southward magnetized CME just crushed it.
Violently crushed it inward.
So how far inward are we talking? Give us the numbers again because they're just staggering.
The outer boundary was forcefully compressed down to an altitude of just 9,600 kilometers above the Earth's surface.
9,600, that's
an astonishingly low altitude. To put that in perspective, that's barely above medium Earth orbit, MEO, which is where a lot of our key GPS satellites operate.
So if I'm doing the math right, the plasmasphere's radius shrank by over 75%. The whole protective layer collapsed to about 1/5 of its normal size.
About 1/5 of its volume, yes.
In just 9 hours. Does the data give us any insight into the physics that drove that incredibly fast collapse?
It does. It's driven by something called the enhanced convection electric field.
Okay, what's that?
It's generated by that magnetic reconnection we talked about. When the southward brose tears open the magnetosphere, it drives this massive short-circuit current across the polar caps. And that creates these incredibly powerful electric fields.
And those electric fields are what strip the plasma away.
Exactly. They act like a massive centrifuge. Plasma inside the magnetosphere gets caught in this flow and is rapidly spun towards the outer boundary where it just gets stripped away by the solar wind.
So the boundary gets pushed dramatically inward.
Dramatically. It carves out that immense plasma layer and just leaves this depleted inner region. The fact that it happened in only 9 hours It just shows you the incredible strength of those storm time electric fields.
And this isn't just a theory, right? This is a measured physical reality. This is the big scientific achievement here, moving from models to direct measurement.
That's the leap forward. Before Gannon, we had data from smaller storms, sure, but getting continuous high-res in-situ measurements from inside the collapsing plasmasphere during a G5 event, that was basically impossible.
The satellites were in the wrong place, or we didn't have the right instruments.
Precisely. The Gannon event just provided this unprecedented level of detail.
And having that detail, knowing exactly how that boundary moves and how fast, that's absolutely critical for future planning, isn't it?
It's the difference between guessing and predicting. It really is. Knowing a storm this intense can drive the plasmapods down to 9,600 kilometers, right into key operational orbits, that lets engineers build better resilience into future satellites.
So it tells you how much radiation shielding you need, where you're likely to get these electrical surges.
Exactly. It moves space weather forecasting from a sort of qualitative, hey, a storm is coming, to a quantitative risk assessment tool. The risk at this orbit will be X for Y number of hours. That's the goal.
The success of this study really seems to hinge on just being in the right place at the right time, hitting a scientific lottery almost.
That's a good way to put it. A 20-year storm hits right when you have the perfect instruments in the perfect position.
So let's talk about the key instrument here, the Arase satellite.
The Arase satellite was the hero of this whole observation. It's a JAXA mission launched back in 2016.
JAXA is the Japanese space agency.
Right. And its name, Arase, actually means rough sea or stormy sea.
How fitting.
Incredibly fitting. Its whole mission is specialized. It flies in this elliptical orbit that dips low through the inner magnetosphere and then swings way out through the heart of the plasmasphere. It's designed specifically to study how this region responds to storms.
So what instruments on Arase actually confirmed that the boundary collapsed from 44,000 kilometers down to 9,600?
The most critical data came from its suite of plasma and wave instruments, specifically the plasma wave experiment and the soft electron and ion spectrometer.
And what do those do?
They're designed to measure the density, the temperature, and the composition of the plasma in real time. So as that plasma pause swept past Arase's orbit, the satellite recorded this abrupt, several orders of magnitude drop in the cold plasma density.
So it flew right through the boundary.
It flew right through it and measured the cliff edge drop. That confirmed the boundary had retreated sharply to an altitude below its position.
So Arase gave us the direct in-place evidence of the shield collapsing. But the team at Nagoya University, led by Dr. Atsuki Shinbori, they did more than that. They synchronized the satellite data with ground-based measurements.
Yes, and that dual approach is what made this study so powerful, especially when it came to understanding the recovery.
How so?
Well, they used Arase to track the plasmasphere, but at the same time, they were monitoring the ionosphere, that's the layer below the plasmasphere, using a huge network of ground-based GPS receivers.
How can you use GPS to monitor the ionosphere?
It's actually a really clever method. We can figure out the state of the ionosphere by measuring something called the total electron content, or TEC.
Total electron content.
Right. GPS signals have to travel through the ionosphere to get to a receiver on the ground. The free electrons in the ionosphere cause a tiny but measurable delay in that signal's travel time.
So you measure the delay, and that tells you how many electrons are up there.
Exactly. Using very precise, dual-frequency GPS receivers, scientists can calculate that time delay, and from that, they can quantify the TEC. So if the ionosphere is full of electrons and ions, the delay is high. If it's depleted, the delay is low.
And that's the key link here. The ionosphere is the supply chain.
It's the supply chain. It's where the charged particles that are needed to refill the plasmasphere, those hydrogen ions, are generated and stream upwards.
So if your GPS data shows that the TEC is dropping everywhere,
it means your source material for refilling the plasmasphere is compromised. And the Nagoya team perfectly synchronized the Arase density measurements from space with the ground-based TEC measurements. They proved that the long recovery delay up in space was directly caused by this massive drop in the particle supply from below.
That's incredible. Connecting a satellite flying thousands of kilometers up with a receiver on the ground, all through a tiny signal delay. It shows just how complex space weather observation has become.
It really does. It's not about isolated observations anymore. It's about a unified, system-wide analysis.
And that brings us right to the central mystery of the Gannon storm. The 9-hour compression. Violent, but sort of expected for a storm this big.
Right.
What wasn't expected was how sluggish the recovery was. The shield broke fast, but the repair job took forever. What's the normal recovery time?
Historically, for a moderate or even a strong storm, the plasmasphere starts to refill pretty quickly. It usually gets back to pre-storm density levels within, say, a day or two.
So 24 to 48 hours?
About that, yeah. The magnetic field bounces back, the electric field weakens, and the natural flow of plasma from the ionosphere starts replenishing those depleted regions.
But with Gannon, that process stretched over 4 full days.
4 days, which is at least double the typical recovery time. It's the longest sustained depletion that Arase has observed since its mission began in 2017.
So why? Why did the supply chain just dry up for so long?
This is where the physics of the compression gives way to the invisible but incredibly powerful chemistry of the upper atmosphere.
Chemistry, not physics.
Right. The critical mechanism delaying everything is a phenomenon we call the negative storm.
Okay, a negative storm. Let's define that, because it sounds like a particle drought, but you're saying it's caused by the storm's energy, not a lack of it.
That's the paradox of it. The superstorm injects an immense amount of energy into the polar regions. That energy is mostly from accelerated particles and strong electric currents. It intensely heats the upper layer of the atmosphere, the thermosphere. That heating is the trigger.
How does heating the atmosphere cause a drought of charged particles? It feels counterintuitive.
It does. The heating fundamentally changes the atmospheric composition. It's a process called upwelling. Normally, the ionosphere is dominated by lighter atoms like atomic oxygen and hydrogen.
Okay.
But the intense heating near the poles causes that neutral atmosphere to expand and rise. And as it rises, it drags up heavier molecular gases from lower altitudes, mostly molecular nitrogen, N2, and molecular oxygen, O2.
So the storm basically pumps heavy gas molecules up into a region where they don't normally belong.
Exactly. It completely changes the chemical balance. And these heavier molecules, N2 and O2, they're incredibly effective at capturing free electrons. It's a process called recombination.
So they basically mop up all the free charges.
They act like a massive chemical drain. The rate at which free electrons recombine with positive ions just accelerates dramatically. So all the electrons and positive ions that should be available to stream up and refill the plasmasphere, you're just rapidly getting neutralized back into plain old gas molecules.
So just to be clear, if the storm had only compressed the magnetic field, the recovery would have been pretty quick.
It would have been.
But because the storm also caused this chemical shift, this upwelling of heavy gas, it broke the particle production line.
It broke the supply chain by destroying the raw materials. The key raw material for refilling the plasmasphere is the atomic oxygen ion, O+, and O+ reacts with hydrogen to produce the lighter hydrogen ions, H+ meet, that stream upward. But when the ionospheres are suddenly flooded with N2 and O2, the O+ ions just rapidly recombine with them instead. It stops them from producing the H+ needed for the refill.
And this negative storm effect, it wasn't just at the poles, was it? It spread.
It spread globally. The data shows that the changes in atmospheric circulation driven by that intense polar heating rapidly transported this chemically altered air mass across vast areas down towards the equator.
Which is why the GPS network saw that tech drop everywhere.
Precisely. That widespread depletion ensured that the plasmasphere's refill mechanism was compromised not just locally, but globally for 4 straight days.
And this link, this is the big takeaway, isn't it? Had we ever empirically documented this exact sequence before? The heating, the upwelling, the recombination, leading to a 4-day depletion?
We had theoretical models that suggested this could happen, but the Gannon storm provided the definitive, continuous, multi-layer proof.
The smoking gun.
The smoking gun. The simultaneous data from Arase in space and the GPS network on the ground offered irrefutable proof. It's the negative storm's chemical control over the system's recovery speed. And this is a huge realization for space weather forecasting.
Why?
Because it means the threat level stays high long after the initial solar shock has passed. The true duration of risk is dictated by upper atmospheric chemistry, not just plasma physics.
Okay, so let's shift from that invisible chemistry to the visible drama and the real-world damage. The compression of the shield was so extreme that millions of people got this breathtaking spectacle. Auroras, way outside their normal homes.
That was the most obvious sign of the storm's intensity. Normally, auroras are confined to these narrow bands around the magnetic poles, usually above 60 degrees latitude.
The auroral ovals.
Exactly. That's because the magnetic field funnels the incoming charged particles into the atmosphere at those specific points.
But during Gannon, the field was so compressed that it allowed those particles to get in much deeper, much closer to the equator.
That's right. When the field is squashed down to 9,600 kilometers, the field lines get warped and stretched. And it effectively widens the area where particles can rain down into the atmosphere.
And that led to photos of auroras in places like...
We saw reports and incredible photos from places like Rikubetsu in Japan, which is mid-latitude, even as far south as Mexico and across southern Europe.
Which is just unheard of.
It's a clear historical marker. When you see red and green aurora displays from those regions, it tells you one thing. The farther the aurora travels from the poles, the stronger the geomagnetic storm was.
Okay, so that's the beautiful visible side. Now let's talk about the ugly, invisible technological impact that lasted for that whole 4-day recovery.
Right. When the plasmasphere is gone and the ionosphere is chemically compromised, our technology is put under serious stress.
Let's start with satellites. What happened to them?
The stress was widespread. Satellites in low and medium Earth orbit experienced significant electrical issues. When that shield collapses, the flux of high-energy particles just shoots up.
And that causes...
It leads to surface charging and internal charging of satellite components. This can cause electrical glitches, system resets, and in some severe cases reported during Gannon, satellites just temporarily stop transmitting data altogether.
And that heating of the thermosphere we talked about, that has a physical effect too, right?
It absolutely does. When the thermosphere heats up, it expands, which increases the atmospheric density at those low orbit altitudes.
Which means more drag.
Significantly more atmospheric drag. For these huge satellite constellations, that drag forces them to burn more fuel to stay in orbit, which shortens their lifespan. It also makes collision avoidance much more complicated.
Now let's talk about the service we all rely on constantly, GPS. People talk about GPS disruption, but what was the specific measurable effect of that 4-day negative storm on navigation accuracy?
The impact was very real and measurable. GPS and other navigation systems, they rely on incredibly precise timing to calculate your location, and that timing has to be corrected for the signal delay caused by the total electron content in the ionosphere.
So, if the tech suddenly plummets during a negative storm, the standard models that the GPS system uses to calculate that delay, they become totally wrong.
Wildly inaccurate. During the Gannon storm and for days after, the models, which are designed for normal conditions, were overestimating the correction needed because the ionosphere was so depleted.
And that caused ranging errors.
Significant ranging errors. For your phone, maybe it means a little inaccuracy, you miss a turn. But for high-precision applications, commercial aviation, autonomous tractors and farming, which need centimeter-level accuracy, that error margin just ballooned to completely unacceptable levels.
And this degradation was measured across the planet for the full 4 days.
For the entire duration of the negative storm, yes.
And what about radio? Things like high-frequency radio used for long-distance communication.
Also broadly affected. The ionosphere is what reflects HF radio waves back to Earth, allowing you to communicate over the horizon. When the chemical balance is disrupted and the particle density changes so dramatically, the reflective properties of the ionosphere change.
You get blackouts.
You get signal fading, dropouts, temporary blackouts across key frequency bands. And because the recovery was so slow, these communication issues were persistent and really hard to mitigate for 4 days.
Which brings us back to the real importance of these findings. Knowing that your technological environment is going to be hostile for 4+ days after a major strike, that's crucial information.
It completely transforms risk assessment. Before this, we might have estimated the risk period to be 48 hours. Now we have empirical evidence that for a G5 event, the chemical fallout prolongs that vulnerability period to at least 96 hours.
So satellite operators need to have contingency plans that last much longer.
Much longer. It means they need to be prepared for a longer period of risk, maybe initiate protective maneuvers for longer than they previously thought necessary. This new clarity on the chemistry is essential preparation for the next big one.
This has been just an incredible deep dive. We've traced this path all the way from a massive solar eruption down to the invisible molecular chemistry that dictates how fast our global technology can recover.
It's quite a journey.
We started with that violent, instantaneous compression of Superstorm Gannon, where Earth's plasma shield just collapsed from 44,000 kilometers down to 9,600 in only 9 hours.
And we ended up understanding this profound vulnerability that was hidden in the aftermath. The real scientific revelation of this storm wasn't just the strength of the punch. It was the sluggishness of the recovery.
That 4-day delay.
That 4-day delay, the longest we've observed since 2017, was directly because of the negative storm, the massive, widespread chemical depletion of the ionosphere.
So to put it simply, the physics of the storm broke the shield fast, but it was the chemistry of the upper atmosphere that delayed the repairs. It just choked off the supply line of particles needed to refill that protective bubble.
And the study gives us the clearest picture we've ever had, thanks to that combined data from the Arase satellite and the ground-based GPS network of the precise link between solar energy, atmospheric chemical changes, and the multi-day vulnerability of our protective environment. It really does alter how we define space weather risk.
So what does this all mean for you, listening right now? It means that when scientists talk about space weather, they're not just talking about magnetic fields anymore. They're talking about atmospheric chemistry that directly affects the stability of your GPS and your communication systems.
Yeah, the protection of our modern world isn't just about how strong the initial shield is. It's about how quickly that particle supply chain can be restored.
So let's leave you with a final thought on that.
If a superstorm that happens only once every 20 to 25 years can cause these measurable, multi-day disruptions to essential services, just consider this. What would the impact look like if we were hit by an even rarer, truly historic event? Something like the 1859 Carrington event, a storm maybe 10 times stronger than Gannon.
Given that our society is just exponentially more reliant on precise, uninterrupted satellite technology today than we were even 25 years ago, that 4-day lag time could easily become a 2-week lag time after a major event.
And that becomes a truly existential infrastructure risk.
Something to mull over the next time you rely on your GPS to get you somewhere.